Okay, everyone, welcome. Welcome to Calculus 2, right? Let me redo this, see where I'm showing up here. It's here. What I'm doing is I'm going to have to do this every single class. I have to come up here and figure out what the camera can see and make sure that I'm within frame. That way the recording will come out good. So I have this much space to work with. So the bad news is I'll be erasing more frequently. But the good news is that while I'm erasing, you can catch up. And then also everything's recorded and will be posted on YouTube later today. Okay, so I want to just give you an idea of how this is going to work. I've never used the camera before. Those of you who've had me before know how I used to do it. I'm trying this because I really want to get up in front of the board and move around. So what I'm going to do is I'm going to show you on this screen over here just what this video is going to turn out to look like. So I have a YouTube channel. How many of you already got on Canvas and watched the orientation video for this class? Okay, if you don't know what I'm talking about, you need to go into Canvas, get into the class. There's a video you need to watch. I go through the whole syllabus. I'm not going to cover the syllabus today. Then you have to do a quiz that says, I've read this syllabus, I understand the requirements of the course, and you submit that quiz. I think it's due Thursday before class. Okay, so, but this is my YouTube channel. There is a link to this in Canvas. And let me show you a video I did earlier today testing this camera out. Give it a second here. Let me just forward to this.
That's doing at the beginning, that pre-record equal to minus square root 1 plus x squared.
Okay, so it's decent quality. I mean, that's through a projector. If you're at home, I'm recording in 720p, 30 frames per second, so it's decent. If I record in 1080p, the file sizes get way too big. I think it's like over 20 gig for one class. This is going to turn out to be like almost 2 gig for one class. So I'm trying to balance how long it takes me to upload the video, how long it takes YouTube to render the video. I think if I do it this way, YouTube should render it within an hour. So, theoretically, you should be able to get to these videos, by 5 o'clock, 6 o'clock today. Okay. All right. So that's what it'll look like. The challenge is going to be that a lot of the things that I show you in this class are going to be up there. So I'm actually going to come and move the camera and put it up there. The reason why is because I also have a Cal 2 Internet class, Hello Internet class. And they are required to watch this video. So I don't want to leave them hanging. I'm like, oh, well, let's look at this. And they're like, still looking at a blank screen over here. So I'm going to move the camera around, and I might even get to a point where I offer bonus points to people and they can rotate and be my cameraman for the day. And if I go over there, they move my camera and then they can move it back to me and move it, That sound like good? Everyone loves bonus points. We can rotate, like who's my volunteer for this class? And then they sit right there and that'll be the designated camera person. Not today though, unless you want to. No, okay. All right. So my name is Robert, sorry. Di Giovanni. And this is Calculus 2. Oh. Cal 2. So what have you all heard about Calculus 2?
Nightmare.
Compared to Cal 1, have you heard anything?
Harder.
It's harder? Y'all heard that?
160 miles per hour.
Yeah, I would agree with that. I think Cal 2 is the bigger of the hurdles. Even when you compare it to Cal 3, a lot of people say Cal 3 is easier than Cal 2. And I mean, really it's because the amount of material we have to cover. There's a lot in this class, so just be prepared. Hit the ground running, okay? That means day one, when I send you home with this homework, you do that homework, you come to class prepared the next day. You know, this is grown-up math, so I shouldn't have to lecture you about that, all right? Like I said, the syllabus is online. The video you can watch, I go through the syllabus. That's all for you to do today. I'm going right to Chapter 3, Section 5. I have lecture notes to hand to you, and we'll start, okay? Yes? Do we want to preview a glimpse into Cal 2, or just get going? What do you want to do? Do you want to see what this is about? Like, I would like to, have you respond to me this semester. That's part of the reason why I'm up here. Like my old students, I used to just be trapped behind that little podium thing. I want to be able to walk around and talk to you. So, you want a little preview? Okay. So, I forgot to do my thing. I'll do it next time. I'm going to have each of you fill out a little card and put it on the table so I can look around and see what your names are, and I'm actually going to call on you throughout the semester. So, I will never learn your names because I'm terrible with names, but at least I can say, Jennifer, what do you think? And I'm going to call people out, and you might get embarrassed, but look, we're here to learn, and if you don't know it, someone else in the class doesn't know it, and, no harm, no foul, right? That's okay. If you don't like that, you can still go to a different class. Not too late. Do y'all want to move that table just a little bit? Because I'm afraid you're going to You sure? Okay. All right, so if we're going to talk about what Cal 2 is, tell me briefly what Cal 1 was about. If you could sum it up. Derivatives, right? That's why Cal 1 is called Differential Calculus. Differential calculus, derivatives, right? Derivatives. The main thing with derivatives, you had to learn the limit first, right? And then after the limit, you had to learn the rules, like power rule, and then the product rule, and then the quotient rule, and the chain rule, and you get all those rules out of the way. Then you start doing some applications, right? So you got all the rules that you have to be comfortable with. Geometrically, Cal 1, the idea was something like if you had a graph, you could theoretically go to this graph and pick a point, let's say A, and then you could find a tangent line right there, and that line would have a slope, and it would be equivalent to the derivative of the function evaluated at A, right? So the pitch of that line was somehow connected to the first derivative of the function. And then the second derivative told you something about concavity, which is, you're frowning or you're smiling, and things like that, right? So what that allowed us to do was take a function and find maximums and minimums, right? And then we did things like optimization problems, farmer builds a pen, things like that. We also learned implicit differentiation, which is where you have two variables in an equation. You can't solve for one of them, so you have to do this thing called implicit differentiation. And when you did that, you did those wonderful related rate problems, right? You have a cone that's being filled with a certain volume per minute or whatever, and blah, 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 right? All those problems. Okay, so that's Cal 1. Cal 2 is what we call integral calculus. Integral calculus, in Cal 1 you probably talked a little bit maybe about antiderivatives, at least in Cal 1. And so Cal 2 is going to take that idea of an antiderivative, which is the reverse process of differentiation. It's going backwards. And we call that integration. And so Cal 2 is a lot about what you can do with those antiderivatives, with those integrals. All right? Let me make sure I'm recording. I am recording. All right. So what sorts of things can we do? We take another look at a curve like this, but instead of looking at tangent lines, we cut this curve off, let's say between 2 points A and B, and we investigate if it is at all possible to find the area below that curve. And then later on, we assign some value to that area. Just like over here, this slope could represent like the instantaneous speed of something at a particular time. This area will have a certain representation, or will represent something depending on what these two axes are. You know, if this is time and this is force, like a force you're applying, then the area would somehow be connected to the total work done in moving an object from one place to another, something like that. But for us, we just want to be able to find that area. Then we'll do something like take that curve, take the same curve, and we will imagine cutting it off again, but wrapping this around the x-axis. So making it a three-dimensional object instead of two-dimensional. And so you get this like shell-looking thing, right? Maybe it might look something like, if I wrap it around the x-axis, here's the x-axis going through the middle of this. Can you kind of agree with me that that's what it would look like if I wrapped it around the x-axis? And then we can imagine, since it's three-dimensional, it has a volume, right? If we imagine that it's solid, that it would have a volume, and so we'd want to know, like, what's the volume of that object. So that's something else we do. Another application in Cal 2 is we'll take this curve and we'll imagine that it's, well, I don't have a string, but imagine it's a string and we take it off the page, we straighten it out, right? Pull it tight, lay it down, and measure the length. So that would give us an arc length. So we'll be able to take a path and we'll be able to measure how long that path is. That's actually more challenging than these other two things. And then we'll also be able to take this and rotate this around the x-axis. And instead of talking about this volume, we can imagine talking about its surface area. So like if we were to paint it, you know, how much paint would we need? Got it? You with me so far? All right. So rotate this around the x-axis. We can also rotate it around the y-axis. We can also rotate it around any line. It does not have to be the x or y-axis. I could take this curve here and rotate it around, let's say, this line right here instead. Would that change the picture? Would it be the same object? If I rotate this curve around here, would it be the same as rotating it around this? To be a little bigger, right? Which means it would have a different volume, which means it would have a different surface area. So we are not going to be restricted to just the x-axis. We'll switch our axes around. So everything I've described here is pretty much going to be the first. Let me look at the calendar here. I have the calendars for everyone. That'll take us all the way through late October. Okay, so somewhere in the neighborhood of Halloween. Okay? All of what I've said. One other thing we'll do is that we'll take a curve. This time we won't bound it. So we'll take something like this. Let me do a bell curve. You've seen these before. Right? You've heard of bell curves before? So these are asymptotes. So the graph is getting closer and closer to those dotted lines. And so the question becomes, is there an area for this? Does this have an area? Is that area underneath this curve finite or not? Or is it infinite? What do you think? It'll depend. It'll just depend on the curve. If the curve decays fast enough, then the area could be finite. If it doesn't decay fast enough, then it could be infinite or unbounded. But we'll look at these. These will be called improper integrals. Another scenario that we run into is something like this, where we have a function, let's say something like y equals 1 over 1 minus x, which looks like this is a rational function. It has a vertical asymptote at 1. So it's undefined at 1. You agree? And let's see, what's happening to the right of it? Like the right of 1. Let's plug a number in here to the right of 1. So like 2. What would we get, a positive or negative number? Negative number. And so I'm not going to go through all of it, but you get something like this on this side, and on this you get something like this. All right? That's what would happen if we graphed it. So what if I asked us to find the area, let's say from here to here? Is it possible to talk about that area? So like underneath this graph, I'm talking about this in here, and then I'm also talking about this area here. Is that infinite area or is it finite? And again, it will depend. So these are called improper integrals because you're dealing with these weird situations where your graphs go forever in each direction or have a vertical asymptote. Kind of make sense? Okay, so that'll be a lot of the, it sounds like that's like most of the class because it takes us to late October. But November is going to be where the true suffering begins because that's when we get into Chapter 8. Chapter 8 is probably the hardest chapter, in my opinion. Chapter 8's, I'll just say series, sequences and series. And this is a very, very interesting chapter. The things that go on in this chapter have repercussions in other math classes, other engineering classes, things that you do here just pop their heads up all over the place. So I'll give you an example of a series. If I take something like 1 plus a half plus a fourth plus an eighth plus a 16th, and I do that forever and never stop, the question becomes, does this add up to be a number or does it become infinite? What do you think? Infinite? We'll take a vote. Let's not be afraid, right? No one's going to get so humiliated today that they're going to drop the class, right? So let's take a vote. How many of you think that this is just going to get bigger and bigger and bigger and go to infinity? Okay. How many of you think that this is going to add up to be a finite number? Okay. So it's kind of, by me asking, it's kind of giving it away a little bit because I wouldn't be asking if it didn't do something weird. This actually becomes, this is a finite number. Right? This has not become infinite. And that's counterintuitive because if you look at this, these are all positive numbers. And if you keep adding positive numbers on top of positive numbers forever, you would think that you can't have a cap to it, right? That you're eventually going to get to, if someone says, well, that never adds up past 10. You would think that eventually you would get to 10 and you just, you'd be able to get past it. Maybe, I don't know. But it turns out it doesn't. And so this is an example of what's called a geometric series, and we can actually figure out what that adds to be. We'll figure it out. Okay? And what this whole chapter really makes you start to think about some strange things. It's a lot different than the other parts of calculus where it's a lot of okay, you find the derivative, you use the rule, you get a result. This is really going to ask you to find patterns in things, and that's a lot more challenging because it's hard to teach that pattern recognition. So, okay. I'll show you another series that is very, very weird. So what do you think about this one? Does this add up to be a number? Does it become infinite? Does it do something else? 0? 1 or 0? Right? It kind of depends. Like if you just look at the first one by itself, it's 1. But if you do the first two added together, it's 0. And then you add that one, it's 1, and then 0, and then 1, and then 0, and then 1. Right? So, interesting. I wonder what it does. I'll show you something on this. Shit, see, I always do this. I start talking for 20 minutes. I don't have time for anything else later. Let's just call this S, okay? All right? Let's call that S for the sum, whatever it is. I don't know what it is. Then what's 1 minus S? Okay, it's 1 minus this, right? Which is, I'm going to put in parentheses, 1 minus 1 plus 1 minus 1 plus 1, right? Minus 1 plus dot, 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 forever, yes? All right, distribute the negative through. And what do you get? You get 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus, right? Don't you? But what is 1 minus 1 plus 1 minus 1 plus 1 minus 1? It's s, isn't it? So aren't we saying that 1 minus s is equal to s? Which means that 1 is equal to what? 1 is equal to 2s, just adding s to both sides. So what's s? A half. What? It's kind of like the average value of the two things you thought it could be, right? 0 and 1. It's like the average value. Now, I'll tell you right now that a mathematician, and in this class, we will say that this series diverges, all right? But in physics, this sum is used a lot, and they actually use 1/2 because they're experimental. When they run experiments, they get series that behave this way, and they can show experimentally that this is the result they're getting. So they use this in physics as the sum. It's kind of weird. There's another one. I'd see if I can remember. I haven't looked at it in a while. It's something like this. 1 plus 2. Oh, wait a minute. Hold on. Is it plus? Ah, shoot. I don't remember. Sorry. It's either, I think it's this. We could work it out, but I don't have time. That this is equal to negative 1/12. I want to say there are pluses between all those, but again, it's something that doesn't really make a lot of sense that it would be this. So, okay, so series are really interesting, and we'll get into those pretty deeply. And by the time we get to chapter 8, I said it's the hardest chapter. By the time we get to chapter 8, usually the people who are still in the class can handle it, you know, because they've proven through the other stuff that they're ready. You know what I'm saying? The first part of the class, the first, a couple of weeks, all we're going to be doing is learning how to find antiderivatives. How to do that. It's called the techniques of integration. And that's a pretty tough section also, but we'll see how you do. All right, so that's just a basic glimpse. We do some other stuff in polar coordinates and parametric curves at the very end of the term, but we only spend like maybe 2 days on that, 2 or 3 days. Please take one of these and pass these back. These are on the website in Canvas. It's the schedule. I'll let everybody get a copy. It kind of lays out the day by day, blow by blow of how things are going to go, okay? Okay. Where? Back there? Can you just hand that back, please? You'll slide those back. All right. So let's get started. Or unless there's any questions or comments. When are my office hours? Anybody know when my office hours are? I have them before this class from, I thought it was 11 to 1. 11 to 1 before this class. I'm in my office. You can walk in and you can get help. And then immediately after this class, from what, 3 to 4? Yeah. 3 to 4, I'm in my class, or in my office to help you. All right? You need more? I think I handed more that way. The notes? No? This pack of notes? Oh, man. Really? That's it? I saw notes sitting on the copier. I thought I accidentally printed them twice, but I guess someone had split my stack up. All right, well, for those of you over here, I guess y'all don't get them. Sorry. But they're going to be up here. So These are all online, by the way. These are in Canvas. I'll bring extra copies next time. These are in Canvas. You can print these out. You can bring them to class and reference them, okay? You need a seat, sir. Let's try and find you a home. Do we not have any more desks here? Well, there's a spot right here. I don't know if you want to get that close or not, but you know, can we slide this desk a little this way? Because I'm kind of pinning that camera up. There you go. Thank you. Nobody has any questions about anything? No? Anything you want to talk about before we get started? I'm wondering if this camera is going to get in the way of you guys. I don't know. You just have to let me know. What the hell is that thing? There it is. All right, so let's begin. We're going to talk about one-to-one functions. So we're in Chapter 3, Section 5. In Cal 1, you went way past Chapter 3, so you may have seen some of this before. So one-to-one function has to pass the vertical line test, right? To be a one-to-one. And if it passes the vertical line test, then that means the function has an inverse. Some examples of one-to-one functions are not illustrated here. Vertical line test, yes, it is a function. Horizontal line test, I said vertical, didn't I? Has to pass the horizontal line test to have an inverse. Okay, so the classic trig function sine of x does not pass the horizontal line test, so it does not have an inverse. Would you agree? If I look at that, it does not have an inverse. If you look at the cosine function, it does not have an inverse. The tangent function is periodic, right? Just like all the others, and it does not have an inverse because if you draw horizontal lines, you'll hit a bunch of times. And we could look at all the different trig functions. The cosecant, if you remember the cosecant was the reciprocal of sine, wasn't it? And you can actually graph sine at the same time, and remember that those little parabola-looking things were always at the peaks and valleys of the sine function. That's where they occurred. And then you had vertical asymptotes that occurred at the x-intercepts of the sine function. Remember this from pre-cal? It's been a while. Okay. Cosecant is the same as secant, except you work off of the cosine function instead. So secant, again, does not have an inverse. And then cotangent's the last one. Cotangent looks like tangent, but it goes the other way, and then the vertical asymptotes are at different places also. So I expect everyone here to be familiar with all 6 trig functions. You should know what they look like. You should know their domains, their ranges, their periods, all that good stuff. There's a set of formula sheets on the website on Canvas that you're allowed to print for this class. I think it's 6 pages. It includes pictures of all of these functions. So you just need to know how to reference it. Okay, I don't necessarily expect you to know right offhand the period of cotangent, but if you do know it, great. All right, so those are our basic trig functions. So how are we going to get around trying to come up with an inverse function for sine? Because that's what this section is about. It's the inverse trig functions. So if I know that sine doesn't pass the horizontal line test, how can I make it so that it does? I cut it off. So what we do is we restrict the sine function. In order to force it to be a one-to-one, we must restrict its domain. So here is an example of me restricting sine. So let me bring sine back in here. There's the sine curve. And what I've done is I've cut off everything left and right. I've just included the stuff between negative pi over 2 and pi over 2. Just that one little piece. If I do that, then that piece right there is a function, and it does have an inverse because it passes the horizontal line test, doesn't it? Also, what's important to keep in mind is that the entire range of the sine function is included in here. So from -1 all the way up to 1, that's all included in the picture. All right? Is that the only one I could have used, though? No. How about this? How about if I took, there's the sine function, what if I took this back piece over there? That passes vertical and horizontal line test. And again, it includes the entire range, -1 to 1. Everything's there. So why not use that piece instead? We could. There's actually infinitely many ways we could have done this. I could have taken another piece of it over there. But what we do is we have to agree as a group, as humans, as math people. We have to agree what is the piece that we're going to cut. And we all agreed that it's this one. And so with that, we can define the inverse sine function, or what's called the arcsine function. So these two notations here, right? Arcsine, or sine with a little -1, is the name of the inverse function of sine. We must restrict the domain of sine, though, between -π/2 and π/2. Everyone clear on that? The only way you can ever talk about an inverse sine function is if you're restricting the sine curve between -π/2 and π/2. If we do that, then we have the following. The inverse sine of x is equal to y. What does this mean? Arrows both ways. If and only if, that's what the double arrows mean. It means implications in both directions. So the inverse sine of x equals y if and only if the sine of y equals x. Notice how the x and y switch places there. We must make sure that the y we're talking about, which is this piece that's in sine, is between -π/2 and π/2. Now, the thing that you put inside of sine is called the argument of sine, but it's usually an angle, isn't it? Sine of an angle. So what we're saying is that angle must be restricted between -π/2 and π/2. And I think, oh, this is the other notation. This one I used the sine with the little the little -1, and here I'm using arcsine. It's just two different notations. Be comfortable with both. Here's a picture of the two together. That's just so you can see it. The red one is sine, and the blue one is its inverse. Does anyone remember the property of functions and their inverses when you graph them? Anyone?
They reflect off the they reflect off the line y equals x.
Perfect. Yes. Anytime you graph a function and its inverse on the xy plane, then they should look like reflections of each other over the identity, which is the diagonal line, which is the line y equals x. So they do look that way. Okay, so now I'm going to do some examples. Let's see how this works out here. I'm going back to my board. Let me do some of these. So find arcsine of 1. Find the arcsine of 1. So I'd like for us to be very comfortable in understanding geometrically what we're saying here, all right? Because I don't want you to just break your calculator out and do arcsine of 1. When you plug something into arcsine, right? When you plug something into arcsine, it's going to spit out what? So I'm going to write this underneath this. With arcsine, I'm going to plug in something and it's going to spit out what? So go back up to the notes and take a look. Look at this right here. We said, what do we plug into sine? We always plug what into sine? An angle, right? An angle goes into sine. So that y in the formula, right? The y in the formula is This one right here. That's an angle. So that means x is going to be a number, isn't it? So if you look on the left side of that double implication, inverse sine of x equals y, x is a number, isn't it? So anytime we're dealing with an arc trig function, this is a number, the argument is a number, and what comes out over here is always going to be an angle. So looking back up at this, if we say arc sine of 1, what we're saying is, what angle do you plug into sine, right? We're looking for the angle. That would give you the value of 1. That's what we're looking for. Now, depending on your pre-cal background, you know, that will kind of dictate how you do this. I love to utilize the unit circle because I think the unit circle is the better way to look at trig functions a lot of the time. When you're on the unit circle, all those numbers that go around at the common angles, right? Those were connected to sine and cosine, weren't they? And so what we're saying here is, where is your sine? Where is the value of sine 1? Sine is which coordinate on the unit circle?
Y.
The y coordinate. So you say, well, where's the y coordinate 1? That happens here, right? That's at 0, 1. And so we want the angle that corresponds to that point. And what is that angle? 90 degrees. So you could answer this two ways. You could say 90 degrees or pi over 2, right? Now, we don't really like degrees. We prefer to do everything in radians, so pi over 2 is better. It's not incorrect to say 90 degrees, but we kind of want to wean ourselves off of that a little bit. It's kind of like, do you still use that symbol? No? I mean, degrees, we use it. I'm not saying we don't use it. It's just not preferred as you move on. All right. What about the next one? See if you can get the next one. The next problem is, so I'm doing 3.5 example 1 right now. I know some of you don't have your notes, or don't have the notes. I apologize. How many notes do we have here at this table? Can we share one set of notes? You got, does this table have notes? Y'all don't have the notes? You have? Who doesn't? Could you hand that back? Thank you. That way y'all can at least share that. And the next one, arc sine. I use different notation though. Root 3 over 2. Okay, so next class when you have your name tags up in front of you, I'll just call on somebody and embarrass you. So today I'll let you volunteer. Anyone want to volunteer the answer? Go ahead.
Pi over 3.
Pi over 3. And that's because you're saying again, where's the y coordinate root 3 over 2? The y coordinate is root 3 over 2 here, right? Yes? What's that point? It's 1/2 root 3 over 2? Something like that. Trying to just make sure this is coming out. But wait a minute, isn't there another point over here that has the same y coordinate? Negative 1/2 root 3 over 2? That one has the same y coordinate, doesn't it? So why not use that one? I'm restricted because I'm dealing with an inverse trig function, and specifically the inverse sine. As soon as I'm dealing with inverse sine, I'm never allowed to look over here, because our angle has to be restricted between what? Negative pi over 2, where's that? Remember, negative angles go the opposite direction. Negative pi over 2 is down here, and then pi over 2 is straight up. So you're only allowed to be in the first and fourth quadrant in order to spit an answer out. So that's good because it eliminates two possible answers. Let me add a little curveball to this. How about arc sine of negative 1/2? So it's a different problem. Oh yeah, by the way, this was pi over 3, right? This angle was pi over 3, which is why that answer was pi over 3. What about this? So where is your, this is again asking, where is your y coordinate on the unit circle, -1/2? So where is it? Is it right here? Is that it? Yeah, that's the point, √3/2, -1/2, yes? Okay, so what is this angle that goes from here to here? 11 pi over 6. But to get to 11 pi over 6, didn't you have to go through, isn't that bigger than pi over 2? So you can't go this way to get that answer. You have to go which way? Backwards. So negative pi over 6 instead. So even though 11 pi over 6 will still land you at the same point, that angle is outside of the domain restriction. So our answer here would be negative pi over 6. Any questions on that? That can get a little tricky sometimes. Just remember your angle has to be between here and here. Positive to 90 degrees, negative to 90 degrees, negative to -90 degrees. Or 0 to pi over 2 or 0 to negative pi over 2. All right, moving along. Next note, I'm now on 3.5.4. Oh, no, I'm not. Yes, I am. All right. The inverse trig function. So just like with sine, we can do the same exact thing for cosine, right? That would make sense. Except that our restriction for cosine is different. What is our restriction for cosine? The angle has to be between 0 and pi. I'll show you a picture of that in a second, why we do that. And then for tangent, we can restrict the tangent function between negative pi over 2 and pi over 2 and be able to come up with an inverse also. So sine and tangent have the same domain restriction, but cosine doesn't. All right, the remaining trig functions and their inverses can be found in the book, all right? And all their domain restrictions are in the book. So you can look through that. This is all pre-cal. There's nothing I've done so far that's calculus. Everything we've done is pre-cal. Cancellation property. Remember that, try and make this a little bigger. Remember that if you ever have sine together with arc sine, they basically cancel each other out so long as the x you're plugging in was between -1 and 1. And then if you do it the other way, you do inverse sine, and inside of that you put sine. It'll spit out the x as long as the x was between negative pi over 2 and pi over 2. So I think I'll give you two examples of that. I'm going to give you some examples of that, and then we'll get on to the derivatives. See, this is why I'm going to need a bonus person for the camera, because this is going to be too much of a pain in the ass to go back and forth. So I just want to show you some things that you could potentially get stumbled up on. If I say, what is, which one came first? Sine, let's do that. Sine of arc sine of 4. A lot of people will be like, well, they wipe each other out, right? Sine inverse of x should just be x, so the answer should just be 4, right? That's what people will do. That's incorrect. Why is that incorrect? It's got to be between -1 and 1. And that's, think about this though. Why is it messed up? What does inverse sine of 4 mean? It means what angle do you plug into sine to get 4? And that's not possible because sine's bounded between -1 and 1, right? You're never going to get 4. So this just doesn't make any sense, right? So this basically would have, doesn't exist, domain restriction, fail, whatever, all right? It doesn't work. The next one that you could potentially get tripped up on would be something like this. Because again, you look at the property, you're like, they wipe each other out, right? Yeah, they're gone. You just get what, 7 pi over 6? But that's not right either. Because the angle that comes out of an arc sine must always be between negative pi over 2 and pi over 2, right? Always. So I can't say 7 pi over 6 because that's outside of that bound. Agreed? So how do I do this? What is the answer? This one you can do just by taking it piece by piece. Look at the inside. 7 pi over 6 is here, isn't it? That's 7 pi over 6? What is sine of 7 pi over 6? So what is the y coordinate at this point? Negative 1/2. Yes? So what I could do is I could rewrite this problem as arc sine of negative 1/2. And now this inside piece doesn't matter anymore. And what I'm doing now is I'm just looking at this and I'm saying cut off this left side because I am now in a domain restriction because of the arc sine. And I'm saying what angle spits out, what angle do I plug into sine to spit out negative 1/2? And that was this angle, wasn't it? We just did that a little while ago. And what angle is that? Negative pi over 6, right? Negative pi over 6. So this, we're just back at the problem we did a second ago. Any questions? All right, let's look at derivatives. So I'm not going to move the camera because I think my internet students could just look on the notes. It says here that we really, since we've studied inverse trig functions in pre-cal and we're in calculus, what we really want to do here is start to talk about the derivatives of the inverse trig functions, which a lot of times in Cal 1 you don't cover, but depending on what school you are coming from, some Cal 1s would actually talk about the derivatives of the inverse trig function. So some of you may have already seen this. But in order to do derivatives of the trig functions, inverse trig functions, we're going to have to take note of two different things. You're going to need to know how to work with reference triangles. And you're going to need to know how to do implicit differentiation. So I'm putting here, these are the skills that are going to be required for us to be able to do what we need to do here. All right, here we go. 3.5, example 2. I would like us to take y equals the arc sine of x and find y prime. All I'm asking here is for you to tell me what the derivative of arc sine is, right? Arc sine of x, what's its derivative? That's all I want. Well, you could just look at your formulas in the back, in the formula sheets, and it would tell you, but I want to know where that formula came from. So I said you're going to need to be able to do these two things. Draw a reference triangle and use implicit differentiation. So let's see how this goes. First thing I'm going to do is I'm going to rewrite the equation, right, that we're looking at. And I'm going to take sine of both sides. And that's because I have an equation. I can basically compose both sides of the equation with sine. So we are taking sine of both sides, right? We are not multiplying by sin, right? Sin is not a number. That's not the operation we're doing here. We're actually taking sine on both sides of the equation. Now, what will happen on the right-hand side? What will sine of arc sine of x be? It'll be x so long as x is between negative 1 and 1, right? So we have this. So there's my domain restriction. So keep in mind that x has to be between those two numbers as we proceed. All right, now the reason I did this, sine on both sides, is because I actually do know what the derivative of sine is, don't I? From Cal 1. The derivative of sine of something is cosine of it, right? So I'm going to take the derivative on the left side and the right side implicitly with respect to x. So derivative of sine of y is cosine y, drum roll, y prime, times y prime. Now, where does the y prime come from that I'm multiplying here? That's chain rule, right? You have to then go inside and take derivative of what was inside sine. In this case, derivative of y is not 1, it's the derivative of y, which is y prime. So there's the chain rule on the left side. On the right side, what is the derivative of x with respect to x? 1. That is 1. Now remember, what is it we were trying to solve for? Y prime. Here's y prime. Can I get rid of the cosine y on the left side? Yes, divide both sides by it. So y prime is equal to 1 over cosine y. Now, you could argue that you have an answer because you have y prime. The problem is that y prime is in terms of y. Most of the time when we took derivatives of functions like over here, we had y, our answer would be like in terms of x, right? If you had y is x squared, the derivative was 2x. We want our derivative to have x in it, not y in it. So somehow I need to recover x from this information. And this is where the reference triangle comes in. So I've already done the implicit differentiation in the problem. Now I'm going to use a reference triangle. So watch how I'm going to do my reference triangle. What I'm going to do is I'm going to go back to the point in the problem where, before I took the derivative, where I had some information that connected x and y together. Specifically here, I had that sine of y was x, right? Now I'm going to draw an arbitrary right triangle. And this is going to be what I call my reference triangle. Now, if you look at this equation and write it down like this, but rewrite x as being the fraction x over 1, then you could say sine of an angle is equal to, what is sine in terms of a right triangle? Opposite over hypotenuse, right? So couldn't you say that sine of the angle y is this opposite side over this hypotenuse? So if I take that equation, I could translate it into this picture. Do you agree? That equation becomes that picture. Any questions? Come on. It's your money. It's your time. Well, maybe it's taxpayers' money. I don't know, but no questions? No one's going to be brave. Okay. Sine is that. Sine of y equals x over 1 means I can draw that picture. Now, look at what we want to find. What do we want to find? Cosine of y. And you know what? Isn't 1 over cosine of y, isn't that just secant? That's just secant y, isn't it? So I would like to know what secant of y is. Secant of an angle is the reciprocal of what? Cosine, right, from that. What's cosine of this triangle? It would be adjacent over hypotenuse. I want hypotenuse over adjacent, don't I? So I need to solve for this side of this triangle. But if you have two sides of a right triangle, you can always get the third, can't you? Can I trust that you could solve for this on your own? What is it? Maybe I should solve it just because it's day 1. All right, I'm going to call it a for adjacent side. A squared plus x squared is equal to 1 squared. Pythagorean identity. Can you solve for a? Square root both sides. Do I take the negative and positive case? No, just the positive because a here is a positive number, isn't it? It's the length of the side of the triangle there. So this A is this. And that's it, right? So what is secant y? We said it was cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So shouldn't I just take 1 and divide it by that? And that's the answer. Question? I see squinting and wrinkled brows, but I'm not getting any questions. That's a formula. It's in your book. It's also on your formula sheets. The derivative of the arc sine of x, which isn't up here anymore, the derivative of arc sine of x is 1 over the square root of 1 minus x squared. Okay? That's what it is. Now you could do the same exact process to find the derivative of arc cosine of x, arc tangent of x, all the other three, arc secant, arc cosecant, all of those, you could do the same exact process. They all require some setting up, implicit differentiation, reference triangle, and final result. Okay? Let's see what we have next. Oh, we have another example. I really hope this blue marker comes out good. Do you mind hitting that light back there? Let's turn that light on. Yep, there you go. Yeah, that's good. All right, so let's look at this. What is the derivative? Find d dx, that means the derivative with respect to x, of arc sine of the square root of x squared plus 1. So I showed you what the derivative of arc sine was, right? We just did that. And I'm telling you that the other formulas can be found on your formula sheet and in your books. So you are now allowed to use them, right? You're allowed to use the formulas. You don't have to show it like I did each time. You just needed to see where it came from. So we do have now arc sine of something, but to take the derivative of it means now we have to apply the chain rule, don't we? So we want to be able to kind of like cover up everything here and just be like, okay, what's the arc sine, what's the derivative of arc sine of this, according to the formula? 1 over the square root of 1 minus this squared, right? That's what it is. So I'm going to write that down. Using the chain rule, the derivative of this is 1 over the square root of 1 minus this whole quantity squared. And you know what? Can we make this, hold on, let's make this a minus 1. Just make that a minus 1, please. Change the problem. Are we done? Is that the derivative? We're done? No, because now chain rule says you've taken care of the arc sine. You must now take the derivative of what was there and tack it on through multiplication. So what is the derivative of the square root of that stuff? I'm going to do it kind of slower. It's 1 over 2 times the square root of x squared minus 1 times the derivative of what's inside there, which is 2x. So I'm just finishing off chain rule on this. The derivative of the square root of that is this. The derivative of what's inside is this. So if you need to go back, brush up on your derivatives. The only thing that's new today is this part right here. Everything else is just chain rule you should have seen in Cal 1. This 2 and this 2 cancel.